In our previous lesson, we learned the concept of dynamic memory allocation. We learned about stack and heap in the context of applications memory. In this lesson, we will be looking at various library functions available in C for dynamic memory allocation. We will look through these functions in some code examples. We will be talking about three functions that allocate block of memory on the heap, and these functions are malloc, calloc, and realloc. And we will also be talking about one function that deallocates a block of memory on the heap, and this function is free. Let us first talk about malloc. This is the most frequently used library function for dynamic memory allocation, and the signature or the definition of this function is something like this. This function as argument asks you for the size of the memory block in bytes. This data type, size underscore t, if you are not aware of it, is a data type that stores only positive integer values. So you can think of this particular data type as unsigned integer data type. The size cannot be a negative value, it can either be 0 or a positive value, and to force this kind of behavior we use this particular type. And this function malloc returns a void pointer. We have talked about void pointer in our previous lessons. Malloc returns a void pointer that gives us the address of the first byte in this block, the block of memory that it allocates. So using malloc, you kind of say that, hey, give me a block of memory with these many bytes. Let us say what we have here in the right is the heap section of memory available to us. Each of these partitions are 1 byte. As we know, each byte in the memory has an address. Let us say this bottommost byte has the address 200, and the next byte is 201, and we go on increasing towards the top. I'll mark the address of some of these bytes. Let's say in our code we make a call to malloc something like this, that hey, give me a block of memory that is 4 bytes. Let's say we store the address returned by malloc in a void pointer variable. Now let's assume that this particular rectangular block that we are showing here in the red is what gets allocated against this call to malloc. These are 4 bytes. The starting address is 208. So what will be the address in P? If we want to print the address in P, then what will be the output? The output will be 208. This is cool. Using malloc we are able to allocate some amount of memory, reserve some amount of memory. But why do we reserve memory? We reserve or allocate memory because we want to store some data there. So we do not want to just randomly allocate some number of bytes. So although it is correct to write a statement like this, in practice we would not do so. In practice we would first calculate how much amount of memory we need to store our data. So let's say we want to store an integer, just one integer. So I need a memory block equal to the size of one integer. So we typically use the function size of, which returns us the size of a variable in bytes, to figure out the size of the data type. And then we typically multiply this particular value returned by size of by the number of units that we need. So if we need just one integer, if we need memory for just one integer, this is good. If we need memory for 10 integers, we would write something like this. Give me 10 into size of integer. Integer is a primitive data type. Sometimes you may know that I know that size of integer is 4 bytes. So I can write something like 10 into 4 here. But it's not a good practice to do so. Size of a variable depends upon the compiler, and we would also be using malloc to allocate memory for complex data types. So we must use malloc like this. Total number of bytes should be written as number of elements into size of 1 unit of the data. Let's say we want to have space for 3 integers. I have picked up 3 so that I have enough space to allocate memory in the figure that I'm showing here. Let's say this block of 12 bytes is allocated because size of integer is 4 bytes typically. So this starting address would be 201. Now how do we fill in data here? If you see, malloc returns a void pointer, and void pointer as such cannot be dereferenced. You cannot write a statement something like asterisk p is equal to 2. This is incorrect. You cannot dereference a void pointer. Void pointer in fact is only used as a generic pointer type, which is normally typecasted into a pointer type of a particular data type, and then it is used. Because malloc itself is a generic function to allocate some number of bytes in memory in heap, it does not care whether you are allocating this memory to store character or to store integer or to store any other data type. It simply returns a void pointer to the starting address. To be able to use this block of memory, we first need to typecast this void pointer into a pointer of some data type. So here we will write something like int star p. Instead of picking up a void pointer, we pick up a pointer to integer because we want to operate with integers. So to dereference, we need an integer pointer type. So we do the typecasting here of the void pointer, and now this statement is valid. If we want to assign some value to the second element, second integer in this list, then we will do something like we will dereference the address p plus 1. Let's say we write the value 4 here, and if we want to access the third integer, then we will write something like this. Let's say the value is 6 here. By asking for a memory block for 3 integers, we are basically creating an array of integers with 3 elements. We could also write this asterisk p as p0, and we could also write asterisk p plus 1 as p1, and similarly asterisk p plus 2 as p2. They mean the same. All the manipulation on dynamically allocated memory happens through pointers. You have a pointer to the starting address, and then if you want to go to the next element in the array, you increment the pointer, and this is how things happen. We have 2 more functions that allocate block of memory. Let us now talk about calloc. The signature or definition of calloc is something like this. Calloc also does the same stuff as malloc. It is only a slightly different. Calloc also returns a void pointer, but calloc takes 2 arguments instead of 1 argument. It takes 2 arguments. The first argument is the number of elements of a particular data type, and the second argument is the size of the data type. So with malloc, if we have to declare an array of size 3, an integer array of size 3, we would say 3 into size of int. With calloc, we would say something like this. The first argument is how many units of the data type you want, or the number of elements, and the second argument is the size of data type in bytes. There is one more difference between malloc and calloc. When malloc allocates some amount of memory, it does not initialize the bytes with any value. So if you do not fill in any value into these addresses allocated by malloc, you would have some garbage there. But if you allocate memory through calloc, calloc sets all byte positions with value 0. So it also initializes the memory that it allocates to 0. The third function that we want to talk about is realloc. If you have a block of memory, dynamically allocated block of memory, and if you want to change the size of this block of memory, then you can use realloc. The definition or the signature of this particular function is this function takes 2 arguments. The first argument is pointer to the starting address of the existing block, and the second argument is the size of the new block. There can be a couple of cases in realloc. The size of the new block that we want may be larger than the size of the previous block. In that case, machine may create an entirely new block and copy the previous data, whatever bytes was written in the previous block, into the new block. If contiguous or consecutive memory is already available with the existing block, and the existing block may also be extended. Let us now look at some code examples and see what we can do with these 3 functions, and we will discuss the function free in our code itself. I'll write some C code and look at some of the use cases in which we can use dynamic memory allocation. The first use case is, let us say we want to declare an array, and we want to first ask the user the size of the array, and then we want to declare an array exactly of this particular size entered by the user. So let's say I have a variable n, and I write a print statement like enter size of array, and then I input this number n from the console. Now I want to declare an array of size n only. So can I do something like this? Well, no, this particular value in the braces cannot be a variable. This will give you compilation error. We need to know the size of the array. We cannot know the size of the array during runtime. In such a scenario, we can allocate the memory dynamically. So we will write something like int star a is equal to, and we will make a call to malloc to allocate a memory block equal to the size of n integers, and this will again give a compilation error unless we typecast this particular return of malloc to integer pointer. And now we have an array of size n, and we can fill in some data into these dynamically, into the elements of this dynamically allocated array. Let's say we want to put data something like first element is 1 and the second element is 2 and so on. So we will write something like ai is equal to I plus 1. We can print the elements in the array. Let's say we want to pick up size of array as 10. Okay, so the output is as expected. We have 10 elements from 1 to 10. If I give size of array as, let's say, 25, then this is what we get. We get all the elements till 25. If we wanted to use calloc instead of malloc here, the only change in this code would be that we would use calloc here and we would have two arguments. N would separate out as first argument and the second argument would be size of int. And this program will run seamlessly. There is one more difference between malloc and calloc. If we do not use this initialization, then with calloc, as you can see, all the elements are being printed as 0. They are all initialized to 0. But if we were using malloc here, then these elements are not initialized. There is some garbage value at each of these indices in the array. So this is one difference between malloc and calloc. Calloc initializes, fills the value 0 into each byte, while malloc doesn't do this initialization. I'll rewrite this initialization loop again, and now we will talk about free. Any memory that is dynamically allocated remains allocated till the lifetime of the program, till the time the program is executing, unless you explicitly deallocate it. And to deallocate memory allocated using malloc or calloc or realloc, we have the function free, and to the function free you just pass the starting address of the memory block as argument. Now what will happen if I free A? If we free A, then the data from that memory is erased. It may or may not be erased. It actually depends upon your compiler or machine. But that memory will be available for allocation against another call to malloc. Let's see what happens in this case when we are printing after freeing that particular memory block. I give array size as 5, and as you can see, the elements being printed here, there is some garbage value being printed. If this free was not there, we would have printed elements 1, 2, 3, 4, 5 as initialized. Now the obvious question would be, even though we are freeing the memory here, we are able to access the value at that particular memory location using this statement when we are using ai, the element at index I. Well, that is one dangerous thing about pointers. If you know the address, you can look at the value at that address, but you should read and write to that address only if that address is allocated to you. What if that address is not allocated to you, like in this case? Well, you do not know what you are reading or what you are writing and what behavior it will have. It actually depends upon the compiler and the machine. In my case, let's say after freeing we try to access the third element A2 and try to push some value there. Let's see what happens if we run this program. Let's give size of array as 5 again. If you see, even after free we are able to modify the value at this particular address A2. But on some machine, such a program may cause our program to crash. We should always be sure to use the memory that is allocated. Otherwise, it's like shooting in the dark. We do not know what will happen. We will now talk about realloc. If we want to modify the size of a memory block, let's say we have a memory block to store n elements in an array, and we want to extend it to, maybe we want to double the size of the array, or maybe we want to reduce the size of the array to half. For such scenario, we use realloc, and call to realloc will be something like this. Let's say we take another pointer variable b, then to realloc we pass the previous pointer a and size of the new block. So the new block is 2 into n into size of int, and we'll of course do the typecasting here. Okay, now what this call will do is it will create a new memory block of size 2n, and copy the values in the previous block, in the previous memory block A, into this new memory block. How realloc works is that if the size of the new block is greater than the size of the previous block, then if it is possible to extend the previous block, find some consecutive memory with the same block, then the previous block itself is extended. Else, a new block is allocated and the previous block, the content from the previous block is copied and the previous block is deallocated. This will become further clear if I write this print statement. I'll print the previous block address stored in A and the new address stored in B, and I'll also print all the 2n elements in B now. And I'll print each element in the array B in one single line. Let's say size of the array is 5 again. Okay, so the previous block address is 9920128, and if you see, the new address is also same, so it was possible to extend the previous block only. And in B, the first 5 elements are from A and rest 5 elements are garbage value. If we wanted to reduce the array size to, let's say, half, then the same block, the previous block itself, will be reduced. So let's say I want to print the previous block now, the n elements. Now as you can see, the first 2 elements are copied, 1 and 2. They're not copied, in fact, they are there already. The rest 3 are deallocated. When we divide 5 by 2, we take only the integral part. So we kind of deallocate the space for 3 elements here. In fact, if we give the size to be 0 here, all that will happen is that the complete block for A will be deallocated. So this statement will be equivalent to using free upon A. In most cases, we will put the return address by realloc into the same integer pointer. So we can write, instead of writing B here, we can write A also. We can also pass the first argument to realloc as null. If the first argument is null and the second argument is size, and let's say we want to create something like a new block with address, starting address stored in B, then if the first argument is null, then this is equivalent to calling a malloc. This only creates a new block, does not copy anything from the previous block. So realloc can be used with the right arguments as substitute for free as well as substitute for malloc. This was all about malloc, alloc, realloc and free. We will see more code on dynamic memory allocation in the coming lessons. So thanks for watching.